He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
One of the importance of sea ice really to keep the global climate in balance.
Sea ice has got 3 major contributions to Earth's climate.
I can't wait to get out and actually deploy the trackers and go out onto the sea ice.
All the measurements, ultimately what we do is to provide data for sea ice models. That is the only way how we can look into the future.
Kia ora, nau mai haramai, ko Claire Kincannon tēnei. Welcome back to Voice of the Sea Ice, a mini-series about Antarctica and its sea ice. That is, frozen ocean.
Occasionally you just stop and think and go, hang on a minute. I'm standing on 2 metres of ice and under that is the ocean. It goes off and connects the whole planet. All the oceans are connected by the Southern Ocean. So it's kind of mind-blowing.
This is Associate Professor Dr. Inga Smith of the University of Otago. She's an expert in ice-ocean interactions. And even though she's been researching in Antarctica for over a decade, she still gets these moments of just, wow. In last week's episode, we talked about the vastness of Antarctica, had a bit of a geography lesson, and got a quick intro to the different types of ice. Sheet ice, millions of years old, kilometres thick, sitting on land. Shelf ice, hundreds of metres thick, floating on the ocean. And finally, the star of our show, sea ice. The ice that freezes and melts around Antarctica each year. But just as all parts of the Antarctic continent are not the same, not all sea ice is the same. Today we head out on the sea ice near Scott Base to learn about its formation and structure, and why it plays such a major role in the planet's climate system.
Whiteness, the saltiness, and the duvet-like insulating properties.
Whiteness, saltiness, blanketness? Keep these in mind. We'll get back to them. But first, a year in the life of. Sea ice goes through different stages as it forms, depending on time and conditions. As winter approaches, the sun sets, the air temperature drops, and the ocean cools. A baby patch of sea ice is born. It starts life as tiny little crystals. They float to the surface and weakly freeze together. This is called new ice, less than 10 centimetres thick. What form it takes depends on the sea conditions. When it's calm, the crystals bind together in super thin sheets called grease ice. These sheets thicken and grow until they cover the surface of the ocean in an almost elastic crust of ice that bends on waves and swell. In rough waters, the thin sheets get broken up, so the crystals gather into slushy circular discs called pancake ice that bob and bounce and smash against each other. But as it gets colder, they cement together and form a sheet. When the ice reaches between 10 and 30 centimetres thick, it's called young ice. And if it continues to grow thicker than this, it graduates to first-year sea ice. As the name suggests, first-year sea ice has only got 1 winter of growth, though close to the coast, this can get up to 2 metres thick. When Antarctic sea ice peaks in mid to late September, it more than doubles the size of the continent. At the outer edges, the ice never fully firms, staying in weak crystal form. Moving further in, you get drift or pack ice, maybe about 1 metre thick, but constantly changing. Ice floes, which are broken off sections of ice sheet, get pushed around by winds or currents, smashing against each other, rafting or ridging up. But moving closer into the continent, you get land-fast ice, shortened to fast ice. This is a continuous and mostly uniform sheet of ice. It forms along the coast and remains attached to the shore, buttressing the ice shelves and providing crucial habitat for some Antarctic life. After the sun returns and the Antarctic days warm, the sea ice breaks up and melts. But not all of it, as Scott's discovery and Shackleton's endurance expeditions can attest. Both of these ships got stuck in sea ice. Discovery for 2 years, until, coaxed along with explosives, the ice finally let go of its grip. The Endurance got stuck for 10 months before being crushed to splinters by the slow but inevitable force of the sea ice around it. Whatever sea ice survives the heat of the summer sticks around to become multi-year ice, generally thicker than first-year ice. By late February or early March, sea ice is at its minimum. And then the cycle begins again. Inge and her group are interested in what's happening to the fast ice in McMurdo Sound, the patch of the Ross Sea bounded by Ross Island, the Ross Ice Shelf, and the coastline of a part of East Antarctica called Victoria Land. And look, these names. Let me quickly explain. Captain James Clark Ross was an early British Antarctic explorer. The Ross Ice Shelf, Ross Sea, Ross Island are all named after him. The 2 large volcanoes on Ross Island were given the names of his warships, the HMS Terror and HMS Erebus. Archibald McMurdo was a lieutenant on the Terror. So McMurdo Sound is a patch of ocean 90 kilometres long, 55 kilometres wide, an area of just under 5,000 square kilometres. For comparison, the Hauraki Gulf is about 4,000 square kilometres. On the Antarctic continental map, this is a teeny area. So we're zooming in here, but it's because we have to. When it's at its post-winter peak, Antarctic sea ice covers an average of 18.5 million square kilometres. That's larger than Russia. It's 4 million square kilometres larger than Antarctica itself. It's about 2 1/3 Australia's or 71 New Zealand's. However you want to describe it, it's massive. You just can't study it all at once. So scientists break it down into smaller pieces. They try to understand what's happening in one area and feed this back into the bigger picture. And for New Zealand researchers, McMurdo Sound sea ice is the obvious choice. Because to get to it from Scott Base, well, that's just a quick stroll.
Scott Base, this is Inge.
Inge, this is Scott Base, go ahead.
Yes, Scott Base, Claire and I are just going out onto the pressure ridges. We'll call you back at 12.
Copy that, Inge. Scott Base listening. Have a nice walk.
Scott Base sits on a long point coming off Ross Island. Out and to the left is the transition where Island ends and Ross Ice Shelf begins. Remember, the hundreds of metres thick ice shelves stick around all year. But just out front is the ocean. And for most of the year, it's frozen. And here, at this transition between a frozen ocean pushed by tides and currents, and the Ross Ice Shelf on one side, Ross Island on the other, the ice gets squashed and pushed upwards, forming what's called pressure ridges. Beautiful structures of deep blue and white ice towering upwards and folding over like waves, as if the ocean were still moving, just in incredibly slow motion. Flags marking a safe route through the ridges flutter in the breeze as we step out onto the ice.
Yeah, every day is different, every year is different, it looks very different.
Inge points to some thicker looking ice that's been wedged up. It's multi-year ice that has stuck around.
2022, so the sea ice right in front of Scott Base didn't break out the last couple of summers.
Okay. Breaking out is the term for when the fast ice finally gives up its grip on the land, succumbing to the weakening of melting and getting pushed out to sea by wind and currents. It's part of the cycle of the sea ice, and Inge and her team are keen to learn about the physics of it all. Because the massive area sea ice covers, combined with its whiteness, saltiness, and blanketness, makes it kind of a big deal for the planet's climate. This land-fast ice is covered with a layer of snow. And so as you look across the 60-ish kilometres to the Antarctic continent coast, all you see is white.
It's got very high albedo, so albedo is reflectivity, so it's reflecting about 80% of the sunlight when it's got a snow cover. And so that's helping keep Earth cool. Open oceans may be 7% reflective rather than the 80% for this sea ice with snow that we're standing on.
You get this. It's the difference between melting your flip-flops on the scorching hot black sand at Raglan versus strolling in bare feet across the white sand beaches in Coromandel in the summer. Darker surfaces absorb sunlight, but the white snow reflects it back into space. And the blanketness is kind of related to this.
The sea ice and then the snow on top is insulating that heat transfer from the ocean to the atmosphere. And so if you just had open water here, that heat, if it's from sunlight coming in, could go straight into the ocean and warm it up.
This insulation ability is also linked to how sea ice forms, which connects to the saltiness. Because this is the thing that makes sea ice quite different to your regular freshwater ice.
When you freeze seawater, and here it freezes at about minus 1.9 degrees Celsius, the ice can't actually fit the salt ions into the structure, so it pushes most of the salt out.
You hear that? Minus 1.9 degrees. We all know that water freezes at 0 degrees Celsius. I mean, the Celsius scale is based around that. 0 is when water freezes, 100 is when water boils. But, as Inga explains, when you've got salt, and also pressure, in the mix, this changes.
Here it's about probably minus 20 today, so the heat's going from the warm, minus 1.9 is warm, to the cold minus 20 atmosphere, so that's that freezing process. And that ice will get thicker from the bottom down as more and more ice freezes into the bottom.
But remember, as it freezes, there's no space for the salt. So you get this mix of salt-free ice molecules and super salty water, or brine.
It's rejecting this concentrated brine, and it's very salty and very cold. So that'll sink down to the bottom of the seafloor in places, and particularly if it's a very active area of sea ice formation, you can form what's called Antarctic bottom water, and that's the cold, salty water that connects all of the world's oceans. Some people call it the conveyor belt, global conveyor belt, where all the oceans have cold, deep waters going at the bottom and then warmer, fresher waters coming back at the top. So that's how they're all connected.
Because it's cold and dense, this Antarctic bottom water drops down and runs along the slope of the Antarctic continent, and then spreads northwards to fill most of the ocean deeper than 4 kilometres. This is a lot of water. Like, it makes up a third of the volume of the whole ocean. Remember that description of the flux of Antarctic sea ice as like the heartbeat of the world? Well, this is why. Each year, the deep veins of the world's ocean are replenished with cold, dense water flowing down as the sea ice forms. To help study the heartbeat of sea ice here, Inga and her collaborators use a monitoring station, which gets placed into the ice by the Scott-based staff coming into winter.
It's a long probe, it's around 2.5 metres long, and it's got temperature sensors inside it. And so when it's put in through the ice into the ocean, you can see how thick the ice is and where the ocean is. And then as it freezes and grows, it includes more and more of those temperature sensors, and we can start to see the fluctuations in the temperature of the sea ice through the season. But we're particularly interested in the growth rate, how quickly that ice is growing over the winter.
This isn't by the pressure ridges just outside Scott Base. It's a bit further out. When she visits Antarctica, Inga collects sea ice cores near where the monitoring station is placed. These get taken back to the University of Otago for analysis. And what they're analysing is how the ice freezes. And you might be thinking, that doesn't sound all that complicated. Water gets cold, then it turns into a solid. Well, brace yourself. In the lab, in a minus 20 freezer, they take little slices off the cores and view them under a polarised light microscope. This lets them see the structure of the ice crystals. And when you do this, you realise that there are different kinds of sea ice in McMurdo Sound. There's the top layer, formed when the heat moves from the ocean to the air. Inga calls this columnar ice, and its crystals are nice and orderly. And then, below this, the crystals are totally all over the place. This is what's called platelet ice.
That's the type of ice that's connected with what's called supercooled water.
As if minus 1.9 degrees wasn't cold enough. Stand by for supercooled water.
The freezing point of seawater depends on its salinity, but it also depends on the pressure that it's at. And so if it's deeper down, it will have a freezing point that's much lower. So at some depths it might be -2 degrees Celsius. And then if it's coming up to the surface where it's -1.9 degrees Celsius, then it could actually be super cooled. So it could actually be colder than the local freezing point.
Okay, so it's not that much colder. But where is this -2 degrees supercooled water coming from?
As brine is rejected from that sea ice as it's forming, then you have very salty water sinking because it's more dense. And if it comes in contact with the bottom of the ice shelf, which is a giant floating glacier, it's made of compacted snow, then it can melt or dissolve that. That's a normal process that happens all the time. And that then slightly fresher water will be less dense, so it'll rise up along the bottom of the ice shelf.
So it's not yet frozen, but it's primed. They still don't completely understand what happens next, says Inga, but something triggers the supercooled water to snap freeze into small ice crystals called frazzle ice.
And that frazzle ice floats up, attaches to the bottom of the columnar sea ice, so the ice that's grown through heat conduction. And when it does that, it starts to grow in place, and you have these giant crystals that can be the size of your hand or bigger, and they look like leaves. They've got veins and wiggly edges, and they're very, very cool. And then that heat conduction process will keep going, and it will fill in the gaps. So you'll end up with solid ice. If you take a section through at the top, where it's just the columnar ice with the heat conduction, it'll look a bit like carpet, a very ordered structure. And then when you get down into that incorporated platelet ice, it's just chaos. It's just like crystals pointing in every which direction, but it's still pretty solid to walk on. And then if you go deeper, there's what we call the sub-ice platelet layer, where there's those crystals that are all interwoven sitting at the bottom, and they haven't been completely solidified with the water in between.
And you thought ice was just ice.
So there'll be the snow on top, there'll be some columnar ice, there'll be an incorporated platelet ice where those frazzle crystals have attached and been frozen in, and then there'll be the sub-ice platelet layer at the bottom.
Now, to get this platelet layer, you need that cold ice shelf water doing its rising to the surface thing. Which means you don't get platelet ice under all the sea ice in Antarctica.
Pat Langhorne, a few years ago, about 10 years ago, wrote a paper about looking at all the different areas where people had reported platelet ice. And it's a few places around the coast near ice shelves. But it might also be that people just haven't looked in some of the places yet. So it's still a very active area of research. Here in McMurdo Sound, there is a lot of platelet ice. It's very common. And it makes the ice grow more quickly. And therefore it ends up being thicker than we would expect if we were just looking at that heat conduction thermodynamics process. And so it's about 20% thicker.
Emeritus Professor Pat Langhorne is a bit of an Antarctic science legend, and the reason Inga started researching sea ice in the first place. So that's how the sea ice here grows and thickens. What about the other part of the cycle, the melting and breaking out? Well, they want to learn about that too, and to help with that, they're using some sea ice trackers. In one of the labs at Scott Base, Inga is opening a large cardboard box and lifting out one of the 4 trackers to be put out on the ice. It's a 60 centimetre diameter wide hard plastic ball. It takes measurements of GPS location, temperature and conductivity, which is basically a measure of saltiness. PhD candidate Antonia Radelwimmer will study the data they send back in real time via satellite as the breakout happens.
The ice and the trackers start drifting northwards out of the region, and that drift is what we're interested in. So when does it start? Where does it go? And what might be driving it? Is it the ocean? Is it the wind? Does it matter how much other ice is around or not?
These trackers are designed to be okay on ice or in the water. So Antonia should be able to follow their journeys and recreate a picture of what's going on for them. For the first while, they'll just sit on the fast ice with nothing happening. So they'll instruct the trackers to take measurements once only every 12 hours. But they'll dial this up when things start to get interesting.
Last year, when we had a similar project, for the time when they were just breaking out, we had a very high sampling frequency. And what we could actually see with 2 of them was that they broke off on the same ice flow. It was a very large ice flow. It was like 10 kilometers across. But because of our higher sampling frequency, we could see the trackers spinning around each other while that flow rotated. So that's the kind of signal we'd like to pick up when we dial up the frequency.
The batteries are designed to last for up to 2 years. But it's a dangerous life for a sea ice tracker.
They could be crushed between ice floes or underneath ice tongues or, in sea ice that is rafting onto each other. Or maybe they can be swept underneath ice, and then maybe they are still trying to transmit, but we just don't know because the transmissions don't get through anymore. The trackers we had last year, we had 8 of those. 2 of those are still transmitting. We lost the other 6.
Breakout time isn't so bad, says Antonia, so she expects they'll last at least that interesting initial stage.
We'll hopefully get a nice drift pattern from the breakout until it starts refreezing again in winter. And then the best case, of course, would be if they survived winter and went on next season as well.
These 4 trackers were named by some school children around Aotearoa, who may also be keeping an eye on their progress. With the help of a helicopter, Inga and Antonia place them on different locations. One beside the sea ice monitoring station, and the other 3 near the sea ice edge at crossing points of satellite lines. While there, they also took measurements of the snow thickness and the sea ice thickness for their own data, but also to help out some other colleagues. Researchers interested in figuring out how thick all the sea ice is, which is tricky to do because even though most of the salt gets pushed out, not all of it does.
And that makes it very different to freshwater ice. And the thickness of freshwater ice can get easily measured using radar technology. But that is difficult for sea ice, so we need a little bit of a kind of a different technology, and that is electromagnetic induction.
This is Professor Wolfgang Rack, a glaciologist at the University of Canterbury who's been working on this tricky problem for a while now.
We know the area of sea ice very well since several decades, so there are satellites out there to do that. But if we want to know how much ice is out there, we need to also know the thickness, because we need to multiply the area with the thickness, and then we know the volume or the mass of the ice.
Remember those layers that Inga mentioned? Snow on top, then columnar sea ice, then consolidated platelets, then sub-ice platelet layer, then ocean. Ideally, you'd want to pull apart all these layers. You can do it manually in one spot on the ice, but how do you scale that up to 18 million square kilometers?
We need to validate satellite methods because the area is so large. So we cannot only rely on very limited point measurements. Point measurements are important to learn about the process, but to extend that knowledge to larger areas, we rely on airborne measurements.
To take these airborne measurements, Wolfgang and the team used what they call an EM bird, electromagnetic bird, that they hang from the bottom of a helicopter or a plane.
We are emitting a magnetic field into the very conductive seawater underneath, and that induces a small electric current, and that induces another small magnetic field what we can measure, and that gives us information about the distance between our instrument and the seawater. And then we have another instrument on the aircraft, which is a laser, and that is the difference in the distance between the laser measurement and the electromagnetic induction measurement gives us the thickness of the sea ice.
And the EM bird that they use is called Rosie.
So Rosie can be deployed from helicopters and fixed-wing aircrafts. It's a little bit easier from helicopters, but we are restricted to operate with helicopters above landfast sea ice because of health and safety. So if we want to cover larger areas, especially very dynamic pack ice out in the Ross Sea, we rely on fixed-wing aircrafts.
Rosie has been used to take measurements of the fast ice thickness around McMurdo Sound under a helicopter for years. But Wolfgang and his team had a super ambitious project lined up for last year, one of these wild science plans. They had aimed to map the sea ice thickness of about 20% of the entire Antarctic coastline, around 50 hours of flight time, starting at Scott Base and ending at the Australians' Casey Station. The plane came from Canada, the EM bird came from Germany. They were collaborating with the Australian Antarctic program and would stop at Italian and French bases along the way. When I first speak to him, they're doing final tests and due to start flying any day. But
unfortunately and unexpectedly, we could not get it to work like in many seasons before. There were some modifications to the instruments which should have improved our measurements and the signal. But unfortunately, it turned out that there were probably some components in that airborne instrumentation damaged, maybe during transport. We do not know exactly.
You can probably hear how totally crushed Wolfgang is. The whole team were. By the time we did the second interview, they had spent weeks trying to fix Rosie.
Despite all the technology and all the communication what we have, we are still far away from civilization in a way that it is still the case that sometimes from that place we cannot work out or repair things what we otherwise probably would be able to figure out back home.
I guess this is the flip side of designing ambitious science projects in Antarctica. Like Scott and Shackleton, sometimes things just don't work out as you had planned.
It was huge support from the various Antarctic programs, so everything lined up very well, which is a very difficult thing to organize and to do, and it seemed to be possible with the support of so many, which is why it is really, really disappointing that we had these troubles. Yes, we will try to repeat at least some parts of these measurements. I think it's very important to do that.
There were some other sea ice thickness projects that did go well. The team put out an instrument to investigate the interaction between sea ice and ice shelf, and they used a skidoo kitted out with radar and EM to get measurements of the thickness of the snow and the sub-ice platelet layer in different parts of McMurdo Sound. And as well as providing data for sea ice growth models, these snow and platelet layer measurements will help in figuring out what's going on with the base of the food web that powers all life in Antarctica.
Oh, phytoplankton, who we should be thanking, making air okay to breathe.
That's next time on Voice of the Sea Ice. Thanks to Dr. Inge Smith and Antonia Radelwimmer of the University of Otago and Professor Wolfgang Rack of the University of Canterbury. Reporting for this series was supported by Antarctica New Zealand's Community Engagement Programme. Thanks to Megan Nicol for her help on the ice and to Anthony Powell for audio recordings. Production help for this episode was from Ellen Rikers, editing by William Ray, sound design and engineering by William Saunders, and additional sound design by Steve Burridge. This episode includes some sound effects from the BBC Sound Effect Library. Learn more about the physics of sea ice and see what the pressure ridges outside of Scott Base look like on the webpage for this episode. You can find that at rnz.co.nz/OCW. Tēnā koe I whakarongo mai. Thanks so much for listening. I'm Claire Kincannon. Have a great week. Kia pai, te wiki.